Hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video in which we are gonna talk about these things. Actually, well, before just getting into the video, let me just ask you a question. Can you prove all of these? And please be honest and write down the answer to this question in the comment section right now. Just have a look at these 6 identities or these 6 integrals and their results. I'm telling you to prove this integral, that integral of sine of x dx is negative cosine of x. Can you prove that down by your own? Or the integral of e to the x is e to the x itself, or the integral of a to the x, where is a constant, is a to the x over ln of a. Can you prove them down? And according to my observation, even I was one of them who didn't really care about these things, because these things are proven, or these things are yeah, it's right. So let's just memorize them. Why do we need to care about the proof? But it's not like that. I was also a kind of student when when I began studying the calculus or like integration. So I was like, let's just memorize them. Why do we need to care about the proof? Like, oh, I'm sorry, sir, I don't need to care. I'm not gonna ask you the proof. Yeah, just tell me the tricks by which I can just memorize them all. But now I'm a guy who questions everything. So now I'm just questioning this. How would I able to prove them down? Okay. So from now onwards, I'm sorry. From now onwards, I would be just bringing these 6 integrals in 3 parts, in which I would be considering these 2 integrals in the first part, that is this part, and the next part would be these 2 integrals. And the third part, the final part, would be these 3 integrals. And like, look, we are having a lot of integrals, like integral of 1 over 1 plus x square, and that evaluates to arctangent of x, right? Or the integral of 1 over square root 1 minus x square dx, that evaluates to arcsine of x. So yeah, well, by the method that I'm going to use to prove them down, you can use that method to prove these 2 things also, but they are going to be quite complicated. So that is why we know about the use of, for this integral, you just have to plug x equals tangent theta, right? Or for here, you just have to plug x equals sine theta or cosine theta as well. Actually, this is also equal to negative arc cosine of x. So yeah, or this one can also be written as negative arc cotangent of x. So these things are like, we can also prove them down by the method that I'm going to use to prove these 6 integrals. But actually, they are going to be quite complicated. So we ain't going to talk about that. But actually, we know how to integrate them. You know what the crazy part here? Even these kind of integrals are easy to evaluate than these kind of things, because they are not having like use of or something like that to just get sorted out like that. So that's why it's quite, and we need to care about all these things, because it's not like to just memorize everything. We need to care about why does this happening, what's the reason behind this. Okay, so basically let's talk about something, relation of integration and differentiation, right? So basically, integration is all about antiderivative. Like what I'm talking about, let's say that I'm integrating a function, the small f of x dx, and I'm having a capital F of x function. Let's assume that. So it also means that if I'm taking the derivative of the capital F of x, so I'm gonna have the small f of x. And these things I'm going to use here to prove all those 6 integrals down. And you know what? How to take the derivative? It's not like to yeah, we know that we know the derivative of x to the n is n x to the n minus 1. But again, it's not like that. I'm just gonna question how does this happening? Well, if you want, I can prove that down, but not in this video, because we are not here to prove that down. But if you like ask me to prove this relation, this identity, so yeah, I will do that. It's not that difficult. But yeah, you need to know about why does this happening. And we know that the derivative of sine of x is cosine of x. So from here we can say the integral of cosine of x dx is sine of x. Hence proof. No, it's not like that. We ain't gonna do this like that. We're just gonna talk about the derivative, the differentiation, and the definition of differentiation is something like that. Let me just show this to you. Definition of derivative. So let's say I'm just going to take the derivative of a function that is being represented like this is the f dash x means we are taking the derivative, right? So it basically means limit x tends to 0 of f of x plus h minus f of x over h. So this is the definition of derivative, right? And we are just going to use these things in order to just prove all those 6 integrals. I think we should just begin with the most basic, that is the cosine and the sine of integration. So yeah, it's gonna be a quite interesting journey. Okay, so firstly, let's consider as the first integral of cosine of x dx. So we know that it is sine of x. Well, we not consider constant of integration, although it is, but we will just vanish it for some time. Okay, so I'm considering that our small f of x here is cosine of x, as we discussed that here right before, and then the capital F of x is here sine of x. So basically, from antiderivative rule, we can say that we need to have the derivative of the capital F of x. That basically means the derivative with respect to x of sine of x, that should be equal to this small f of x, that is cosine of x. So we need to check that down, and if it is, and hence this is valid, this integral is valid, we just need to check that. So from there I can say that the derivative of sine of x is something like this: f dash x equals limit h tends to 0. Well, here your f of x here is, like for this differentiation case, it is sine, or let's consider the capital F of x. Don't get confused. Capital F of x is sine of x, right? So when we replace, like as we discussed here, that f dash x equals limit h tends to 0 of f of x plus h minus f of x over h. So when we replace like x here with x plus h, so we're gonna have sine of x plus h, and the function as it is, that is minus sine of x over h. And now we just have to solve this limit in order to get the derivative of this one. And you know what? Yeah, let's do that. Okay, so let's do that right over here. So basically let's expand that. We know that the expansion of this sine of x plus h can be expanded something like this. Sine of x plus h can be written as sine of x cosine of h plus sine of h cosine of x. Okay, so it is limit h tends to 0 of sine of x cosine of h plus sine of h cosine of h, and we were having minus sine of x as well, right? Okay, and over h. Fine. Next, f dash x equals limit h tends to 0. Okay, now you know what? Here, okay, yeah, that's fine. So I'm just going to open this parenthesis, and I'm just going to write it as sine of x cosine of h minus sine of x, like this sine of x is here and this one is here, sine of h cosine of h. And I can just do this h here, like I can just do that here. I just separated this one rational part into different rational parts, actually rational numbers, rational quantities actually. Okay, now as you might see here, I'm just going to plug sine of x common out of it, and wait a second, yeah, fine. So okay, so if I'm just going to plug its limit h tends to 0, if I'm just going to plug sine of x out of it, so I'm just going to have cosine of h minus 1 over h, and another limit h tends to 0 of cosine of x and sine of h over h. You know what? There is an identity which I think I should just write that down here. There are two identities which are being applied to there, and you need to have an idea about that. So basically, the first one is limit h tends to 0 of cosine of h minus 1 over h is always 0. So the first identity. And the second one is quite famous actually. Its limit h tends to 0 of sine of h over h is 1. So if you are going to plug them here, since this sine of x and this cosine of x is a constant for this limit, so basically this is going to be 1 and this whole part is going to be 0. So basically we are left with f dash x, we are left with this cosine x only. F dash x comes out to be cosine of x. Okay, hence proved. That was the condition we just wrote down here. Actually, there are some signs which I have the words that I have written. It's not properly erased, but yeah, it is written there that d by dx of sine of x would be equal to cosine of x, and hence the d by dx of sine of x is equal to cosine of x. And from here we can say that finally the conclusion here, the d over dx of sine of x is cosine of x, right, as we proved here. And from antiderivative rule we can say that integral of cosine of x dx equals sine of x. So hence this crazy or this sweet little integral is proved. And believe me guys, the integral of 1 over 1 plus x square, or the integral of 1 over the square root of 1 minus x square, that evaluates to arc tangent of x and arc sine of x respectively. They both were quite, or maybe they both were very easy to evaluate rather than this one, despite this one actually, because this took a lot of things. And now we're just going to talk about the another one. Well, okay, yeah, it's fine. Okay, actually an incident happened with me that I was talking and my recording has stopped because my phone got too much heated up. Actually, that is why I just checked that down whether I'm just talking or is it recording. Yeah, it is recording guys. That is why you can just listen to me all of this the things that I'm talking about. Okay, so now let's talk about the second one for this video. Integral of sine of x dx that evaluates to cosine of x. Okay, so again, from antiderivative rule we can say that the derivative of cosine of x should be equal to minus sine of x. Let's check that out. If it is, then that integral is correct. So how are we going to do that? We know that the derivative rule, the derivative definition, f dash x, well again your capital F of x here is cosine of x for this case. Next, it is limit h tends to 0 of cosine of x plus h minus cosine of x over h. And now again we can expand this a little bit here after using this identity, which says that cosine of x plus h can be expanded as cosine of h, cosine of x, cosine of h minus sine of x, sine of h. Right? Okay. So now we are just going to plug that over there. So f dash x equals limit h tends to 0 of, we're just going to write this down on the place of that. So it is cosine of x, cosine of h minus sine of x, sine of h, and minus cosine of x over h. Okay. Now let's do some changes in this limit. And what are they? Wait a second. Yeah, again we are just gonna have the same two identities that we have talked about in the first integrals evaluation. Here what I have told you to remember that, let me just show you here. So it's limit h tends to 0 of, well, I'm just going to combine this one and this one for a little bit, and from this one and this one we can just say that we can just take common out of cosine of x, and we would be having inside the parenthesis cosine of h minus 1 over h, and then we can write this as minus limit h tends to 0 of sine of x, sine of h over h. Again, this one evaluates to 0 and this one evaluates to 1 basically, and well, we are left with negative times sine of x. So basically, hence again we proved that the derivative of this cosine of x is negative sine of x, and hence like the conclusion again here. So the derivative of cosine of x evaluates to minus sine of x. So hence the integral of sine of x dx evaluates to minus cosine of x. Hence proved, guys. And that is what it is all about, guys. Actually, again my electricity has gone for whatsoever so reason, I'm not sure about that. So that is why, oh my god, it's quite hot out, it's quite warm outside. So that is why I'm just getting sweat. Oh, okay, not getting sweet but getting sweat, I'm sorry. Okay, so like for now I think it's fine. As I promised you guys, I will just make 2 videos more on the evaluation of the, or maybe I would like to just request you something here, because now till now you are sure what we have to do to prove that those kind of integrals. So I would like you to just perform some of your activities in those 4 integrals that we're left with. So that would be a great thing if you are just practicing them and prove it by your own. And if you've done that, please just comment that down. I would feel that yeah, I did. I just I taught you something by which you proved a great thing. This is great. It's not a child's play. It is great. And these things are not easy actually, right? And I have never heard about any teacher, any academic teacher proving these integrals down. So it's a great thing actually. And you know what? In colleges, there are a lot of proofs. Like if we talk about some bachelors of science or bachelors of mathematics, so we need to get about a lot of proofs. So let's be pre-prepared here. Okay, so I think it's now, and it's now fine, and I think we should just cut off right now, and let's meet up in the next video. Or maybe I have recorded some of my videos on tablet, so maybe I'm just gonna upload them all. Yeah, it's one or two videos, I'm not sure. Actually, an integral video I have made, so I'm just gonna upload that, or maybe I have uploaded that. But yeah, but I'll make sure to just come up with those four integrals as well as fast as possible. Don't worry about that. And yeah, again, if you got to learn something from my video, please make sure to just like and subscribe and share. And again, if you got to have any kind of doubt here, and if you like, yeah, it's proved. So if you got to have any kind of doubt, like why this is happening, how can we do that, and why rather than this one, why we can't go with that method, so you can please just share your thoughts with me. I will read those things, and if I would be able to solve your questions or doubts, so definitely I'll do that as fast as possible. So yeah, thank you so much for watching this video, guys. Goodbye. Be careful. Take care, and fine. Just be cautious for the next video. Wow.